going back, we discussed an example where we said the cost of going for movies was directly proportional to the number of people. But that was a very simplistic view. It is not only dependent on the number of people, it is also proportional to the price of the ticket. Let's say on day 1 the price was 100 and on day 2 the price was 200. I know the overall cost is going to double because the price of the ticket has doubled, right? So individually, or we can say, if I want to elaborate the relationship, the cost is directly proportional or varies directly with the number of people when the price is constant, and it varies directly with price when the number is constant. That means if you want to think about cost and number in your head, you must not think about price, because otherwise you're handling too many variables at the same time, and same thing like this. But this can be put together where cost is proportional to n dot p, the number of people, and is a product, and the price. Okay. Now how will the multiplying factor work? Let's say in your story, on a particular day there were 10 friends, on the other day there were 20 friends, okay? And the price was on one day 50 rupees, on the other day it became 60 rupees. So the cost was, what would be the change in cost, okay? So I can calculate it as 500 and this would be 720, right? Yes, no? No, sorry, 1200. So it has gone from 500 to 1200, okay? But let's see what happens here. I know the multiplying, I know this symbol basically shifts the multiplying factor, or even going backwards, I know this is going to be a constant. So the multiplying factor for numbers is going from 10 to 20, it is getting multiplied by 2, or 20 by 10 is 2. So the multiplying factor for number is 2. The multiplying factor for price is going from 50 to 60. New by old, 60 by 50, 0, 0 gets cancelled, you get 6 by 5. So the multiplying factor for price is 6 by 5, right? Put these two together, what you get as a multiplying factor is 12 by 5, right? Now, because the denominator is getting multiplied by 12 by 5, and you know this relationship does not change, the numerator should also be multiplied by 12 by 5. So let's say if I had given you 500 and what is the new price, right? So you would have done 500, you know the multiplying factor is 12 by 5. In this case we already knew every value, but I hope you understand how the relationship works. Or even more, in just the symbol form, the multiplying factor here is 2, here is 6 by 5. Both of them get shifted here. First they get multiplied with each other and then they shift here. So over and over again, basically this symbol is going to help you shift the multiplying factor. Of course you can also use the equation form, right? You can just remove the proportionality symbol and put a constant there. So this is the data of the equation. If you notice, you have a pair for y, you have a pair for z, new value, old value, new value, old value, new value, or you have the ratio there basically. So the multiplying factor for y is 3, right? 3 into 3 is 9, and the multiplying factor for z also is 3, and you have to figure out the value of x. Multiplying factor for y is 3, z is also 3. 3 into 3 becomes a 9 here. You know this symbol shifts it to this side. So multiplying factor for x is 9, so 2 9s are, we get 18. 2 into 9, you're getting 18. Okay, so this was very, very easy. But if the question was in the other direction, let's say if x was given and y was not given, what I would do first is I would rewrite this equation so that all that I know is on one side. Okay, and my life would have been easier. Multiplying factor for x is 9, multiplying factor for z is 3, 9 by 3 is 3. This symbol simply shifts it, so multiplying factor for y also would have been 3, 3 gives you a 9. Yeah. Now we look at two interesting problems which should cover a wide variety of concepts that we have just discussed. The problems will come on the screen one by one, and then we'll look at the solution. So please take a look at the first one. Yeah. So it says the value of a bar of gold, the weight of which is 400 grams, varies inversely with the square root of the fraction of impurities in it. The fraction of impurity, that would be impurity out of total. So this varies inversely with a fraction. You can just think of it as a, instead of this impurity upon total, you can just call it a F also, but overall that F is going to be impurity upon total. Okay. When there was impurity was 25 grams, the value was 45,000, and it says when the value is 90,000, what is the impurity going to be? Okay. So now, first of all, what you should notice is, if you have got the idea of ratios and multiplying factors, is you have a ratio of value, right? You know the multiplying factor, 45,000 to 90,000, the multiplying factor is 2, okay? So I know the multiplying factor for this side, but everything else is here. So let me rearrange this equation. Can I remove the square root here and put a square here? Yeah. And instead of calling it I by t, which would be cumbersome for me, let's call it the fraction for right now. So the multiplying factor for value is 2, it's getting squared, so it will become 4, and it's inverse, right? So this 4 will go here. That means basically the multiplying factor for the fraction is 1 by 4. Is that okay? Now what is the fraction? So basically from fraction 1 to the fraction 2, you're multiplying by 1 by 4, right? But what was fraction 1? It was impurity 1 over total 1, you can call it. And fraction 2 would have been the new impurity over the new total. But in the story, the total is not changing. The total is 400 grams only. So you can put it here and you can put it here. Impurity 1 was 25. This 400 basically cancels itself, so you could have also not put it. So essentially your new impurity becomes 25 into 1 by 4, which would be how much? 6.25. Okay. We could have done this faster if we understood that in the impurity fraction itself is a numerator by denominator entity, and the denominator is not changing at all, it's constant, okay? So whatever is happening to the fraction is essentially happening to the numerator. So you could have directly applied, you could have thought, okay, the multiplying factor for value is 2, it becomes squared, so it becomes 4, and straight away I take an inverse and I multiply it to the fraction. Fraction is nothing but impurity only because the weight is not changing. So 1/4 of 25 directly gives you 6.25. You could have also done it like this. Or you could have used, of course, used the whole equation form and plugged in values. So the only new part here probably would be this impurity upon total fraction part, which might have thrown you off guard somewhere. Okay. Okay, and the second problem is that the value of a silver coin varies directly as the square of the diameter and when thickness is constant and varies directly as its thickness when the diameter is constant. Okay, so essentially it's a joint variation question. I have two forms. I can merge them together into a very simple that the value, right, the value varies directly with the square of the diameter as well as the thickness. Okay, and the values given, I mean the information given is their diameters are in the ratio 4:3. So D1 and D2, the ratio is 4:3. You can think of it, the multiplying factor is 3/4. Okay. And the question is about the ratio of thickness. So T1 and T2 we have to figure out. So I can just now guess also that the value multiplying factor must also be there, and it says the value of the first coin, is, which represents an equal sign, 4 times the value of the second coin. Okay, so if you want to figure out the ratio, V1 upon V2, if I bring V2 here, is 4/1. Okay, or the ratio of values is 4:1, or the multiplying factor if you want to see is V1 into 1/4, you get V2, right, if I rearrange this. So the multiplying factor for value I know is 1/4. I hope that is clear. You can think of, you can hit pause and think how. The multiplying factor for value is 1/4. I know the multiplying factor for diameter is 3/4, which should be inside the square. But I want the multiplying factor for thickness, or the ratio for thickness. And I know I could have made my life easier if I put, when I was writing this equation, if I had moved this d square here, right? Basic movement. So thickness is directly proportional to value and inversely proportional to d square. So I know the multiplying factor for value is 1/4. The multiplying factor for d is 3/4. Square of that will make it 9/16. Yeah, 1/4 by 9/16 would become 16/9 into 4, or overall 4/9. The overall multiplying factor on this side after working this out is 4/9. I know this symbol shifts it, so the multiplying factor for thickness also would be 4/9. To go from old value to new value, you have to multiply by 4/9. That means 4 is the new value, 9 is the old value, or the ratio is 9:4. You can also think like T1 into 4/9 is equal to T2, but you want T1 by T2, so move T2 here, and this 9 here, and this 4 here, so you get 9/4, which is the same as earlier. So whatever way you think about it. Once again, I would like to mention that you could have also done it by using the K form. V is equal to K d square T, and then plugged in the value of V, d square in T, and then finally got in the value of K. Okay. I'm sure everybody has seen this problem. 10 workers in 10 days can make 10 chairs, let's say. Okay. And the question is 5 workers in 5 days will make how many chairs, or any such question. Okay, this we're just starting off with an example. We'll do a lot of such questions to understand relationship back and forth. So before we start doing this question, let's establish the relationship between these 3 variables: workers, days, and chairs. Okay, and the relationship, if you think about it, is would be something like this: that the chairs are directly proportional to the workers when days are constant. Yes, no? So if you think about it, that means if you do not think about days, the more workers there are, the more chairs will be there. or if the workers are doubled, chairs would be doubled. We assume it's a mathematical universe. We assume nobody cheats, nobody gets tired. Every day they work at the same rate. So if I increase the number of workers, the number of chairs is going to increase. Or I know that their chair upon W relationship is a constant. Are we okay with that? Or I know that whatever is the multiplying factor for workers is going to be the multiplying factor for chair, and vice versa. If I think about it more, chairs are also directly proportional to days when workers are constant. Imagine you're running a workshop and you have a certain number of people who come every day. If let's say if you get 5 days, you'll be able to make some number of chairs. If you get 10 days, you'll be able to make more chairs. You get 15 days, you'll be able to make even more chairs, assuming that workers remain the same and they work at the same rate. In mathematics, the situation does not change much. We can assume that it's going to be constant, okay? So, and we've seen this earlier in the previous question only, it's a case of joint variation. So I can rewrite the relationship as that chairs are directly proportional to workers as well as days. Yeah. Now this question becomes very easy because I already know this relationship. It is nothing but a story form given where I can work out this relationship. Now I have the multiplying factor for workers. Workers are going from 10 to 5. So the multiplying factor would be 5 by 10, which is 1 by 2. So the multiplying factor for workers is 1 by 2. Worker 1 into 1 by 2 is equal to worker 2. Or you can also call it you have the ratio of these two things, okay? The multiplying factor for days is 5 by 10 again, which is 1 by 2, right? So you have the multiplying factor for workers, you have the multiplying factor for days, 1 by 2 and another 1 by 2. So what you know is that the chairs are getting multiplied by 1 by 4, or the product of this, okay? And a smoother way of thinking would be you start with chairs, right? You're starting with old chairs. So you start with old chairs, you have and you know they're going to be multiplying factors, and you will get to the new number of chairs, right? And what are those multiplying factors going to be? Chairs vary directly with workers. The multiplying factor for workers is 1 by 2, so chairs get multiplied by 1 by 2. Chairs vary directly with days also. The multiplying factor for days is 1 by 2. It gets multiplied by another 1 by 2. So it is basically 10 is getting multiplied by 1 by 2 and 1 by 2. I'm keeping this form so that it's visible that this 1 by 2 is happening because of the workers. This 1 by 2 is happening because of the chairs. And finally my new chairs, 10 into 1/4 is going to be 2.5 chairs. So 2.5 chairs are going to be made here, okay? So essentially, I hope you noticed here, this is a language problem, but the concept involved is still that of variation and still shifting of multiplying factors. And if I can get this idea of moving from one number to the other, I know it's very smooth because we're just picking up the multiplying factor and putting it on the variable which we want to find out. We look at 5 or 6 more problems like this. I hope this idea gets very clear in your head, okay? Okay, so let's work with that idea more and confirm it in our heads, okay? So once again, let's say 10 workers in 10 days can make 10 chairs, and you have to make 30 chairs in 5 days. How many extra workers would be needed? Okay, so that's the question here. Now, first of all, let's once again work out the relationship that the chairs are going to be directly proportional to days as well as workers, right? That means chair will get multiplied with the multiplying factor of day and worker and so on and so forth. This relationship if I look at my numbers here, I have the multiplying factor for chairs, which is 3, 10 into 3 gives you 30. I have the multiplying factor for days also, new by old, 5 by 10 is going to be 1 by 2, okay? But I have to work out the multiplying factor for number of workers. So I've learned already that when I have multiplying factors, all variables I should move on one side. So what this also means, which reminds us, is that I can think that workers are inversely proportional to days. And if you think about it, if you're running a workshop, if you increase the number of workers, whatever work you want to get done will get done faster. Does that, I hope that makes sense in your head. So workers and days are inversely proportional. Or if you think in the opposite direction, if you reduce the number of workers in your workshop, the time taken to finish the work will increase, right? The same thing goes for any kind of work involved. So if you decrease the number of workers, the time goes up. If you increase the number of workers, time goes down. So there is an inverse relationship between workers and days, okay? So now I have the multiplying factor for chairs, I have the multiplying factor for days. I want to figure out the value of workers. So I'll start with this 10 because this is the old value. I know the multiplying factor for chairs will also get multiplied to workers, so I know this will get multiplied by 3, right? The multiplying factor for days is 1 by 2, but I know that the workers are inversely proportional to days. So this 1 by 2 should be flipped over, it will become 2 by 1 or just 2. So the number of workers would be 10 into 3 into 2. There is nothing else in the story. So this new number is going to be 60. But my question wasn't how many workers are going to be there. It was how many extra workers are needed. So plus 50, right? You were at 10 workers and you need 60 workers. You need 50 extra workers, okay? So I hope that makes sense. In this case, we're using the inverse relationship. Days and days and the number of workers are inversely related to each other. Therefore, this multiplying factor got switched into 2. So remember this movement of multiplying factors. If you have a 3 by 4 and inverse relationship, it becomes a 4 by 3. So this movement or the flipping of ratio should get very, very comfortable in your head. Okay. Way of reading such problems would be, for example, when you're reading the problem and it says 6 laborers, instead of reading the whole sentence, if you know what kind of problem it is, what you can do is you've seen 6 laborers, straight away in the problem statement look for more laborers, because you know it's a ratios thing, there are going to be pairs involved, right? So 6 laborers and I look for how many laborers. So my question is eventually about number of laborers, so I'll start with 6 into something I know I'm going to work on that, okay? It says 6 laborers can build a wall, and if I scan through the question it says 3 such walls. So first of all there was 1 wall and later in the story there are 3 walls. What is the multiplying factor for walls? 3, right? To go from here to here. Then it says 6 laborers can build a wall in 10 days. And later it becomes 5 days, right? So 10 days and 5 days, the multiplying factor is 1 by 2. And if I read the problem carefully, there is one more thing. It says double the efficiency, right? Double the efficiency. Efficiency is another factor that is coming here. So whatever was the efficiency earlier gets multiplied by 2 and you get the new efficiency, okay? So now step by step, we can write the equation form also, but step by step and commonsensically we'll think what will happen, right? So we have the number of laborers. This was laborers were equal to 6 earlier, right? The wall, which means the overall work has increased. It has gone from 1 to 3. Now think in your head, if the work is increasing, the laborers also have to increase, or would you decrease the laborers? I hope you got the right answer, that you have to increase the number of laborers. That means whatever is the multiplying factor of a wall will also become a multiplying factor for laborers. So 6 into 3 so far, right? So the number of days is getting halved, and if you think about it, days are inversely proportional to laborers. So if the multiplying factor for days is 1 by 2, the multiplying factor for laborers would become 2 by 1, okay? Now lastly, think about the efficiency. This is efficiency, okay? What does efficiency mean? Efficiency is rate of work, right? How much work gets done in each day. Now here it says the efficiency is getting doubled. That means the laborers are doing more work per day, right? So imagine you're running a workshop and some of your workers started working more. Wouldn't you be able to reduce the number of laborers because some of your people are working more than others? Okay, so now laborers, the efficiency or how much work do they do gets doubled. So efficiency is inversely proportional to the number. The more efficient people you have, you can reduce the overall number of people if you have efficient people, right? So when the multiplying factor of efficiency is 2, the multiplying factor for laborers is going to be half, right? So if I just work, and that's it, there is no other variable in the story. If I work this out, overall I'll get 18, which is laborer 2. So initially there were 6 laborers, now there are 18 laborers, 12 laborers are added. I can also figure out the ratio, which is 18 by 6, which is 3 by 1 or 1:3, right?